Okay, we have a last talk for morning session for today. Our speaker is Qiao from the Northwest University. This talk titled by orthogonal approach to exact solution and thermodynamics of the quantum integrable spin chains.
Okay. Okay, and thanks for the introduction. I'm Qiao from Northwest University, the China one, from in Xi'an, right there. Okay. First, I want to thank the conference committee for inviting me to be here to give this talk. And my talk is my collaborators is Professor Wenli Yang and Professor Junmeng Cao, Dr. Pengzheng Lu, now in QU. Okay. This talk mainly contains 4 parts. The first is the motivation, and the second I will take the X model with periodical boundary condition as an example to illustrate our method. And the third part is I will generalize it to the open boundary condition case, which break the UE symmetry of the system. And the last is the summary. Okay, let's begin with the first part, motivation. We know there is a lot of methods to solve quantum integrable systems. For these models with UE symmetry, you can use the traditional coordinated beta ansatz or TQ relation or the algebraic beta ansatz. And for systems without UE symmetry, due to the newly discovered inhomogeneous TQ relation, and many methods has been developed these years, such as the fused-based TQ relation, separation of variables, and modified beta ansatz, and the last, but not least, is off-diagonal beta ansatz. We should comment on this inhomogeneous TQ relation here. We know it has 3 terms, and it will result in 3 terms beta ansatz equation. And this equation is a little bit hard to solve. And the patterns of the beta roots is complex. So in order to find the thermodynamic limit, we have proposed a TW scheme to solve this. And in the TW scheme, the W operator can be neglected in the thermodynamic limit. So this relation will equivalent to the so-called inversion relation. But the proof is absent, so here we can show it. This talk is mainly based on these 2 papers. Okay. Okay. At first, I will show the method with the periodical boundary case. The Hamiltonian, as shown by the Yuan Miao, this is the Heisenberg Hamiltonian, and with periodical boundary condition, and it is integrable because there are enough conserved charges which can be generated by the so-called transfer matrix as this way. And the transfer matrix is constructed by the well-known R matrix. When we take the tensor product of the R matrix, we got the Montrond matrix. Take the trace in the auxiliary space, and we obtain the transfer matrix. And the R matrix satisfies very many useful relations. Here, we should focus on the Fourier relation. And in this relation, when you put the spectral parameter at some specific point, it will degenerate to the project operator. P minus is a one-dimensional antisymmetric project operator, and P plus is a three-dimensional symmetric operator. Okay, the R matrix satisfies the Young-Box relation, and the Mondrian matrix also satisfies this RTT relation. I think you experts are already familiar with this. So this RTT relation directly leads to the commutation relation with of transfer matrix with different spectral parameters. And the Hamiltonian can be written as this way, the logarithm, and take a derivative of this operator. Okay, let's come to the T-up scheme. By using the fusion technique, we can consider a quantity this one and Tu times Tu minus eta. And we embedded this function into two auxiliary space like this one, and we can input an identity here and divide this into two parts. The first part is a function you can directly write, and the second one is an operator. Okay, let's see the details. For the first term, we should consider these operators, which is the fused R matrix with the P minus project operator. When calculating this equation, you get a number or a function here. Times this together, you can obtain the fusion of the Mondrian matrix. It's also a function. For the second term, we use the P plus projector operator. The R matrix, when doing the fusion procedure, you got a new operator, which is 6 times 6 fused R matrix in this form. And the fused Mondrian matrix can directly constructed by the fused R matrix in this way. So the W operator is exactly the fused transfer matrix. Okay, the fused R matrix also satisfies the Young-Box relation. To better understanding the fusion procedure, we use a graphic representation to illustrate it. The R matrix, we can represent it as a cross, like this way, and the Young-Box relation is this figure. Okay. For the recall that the fused R matrix is the definition of the fused R matrix, and we can draw a diagram like this way. This red rectangular, in the rectangular there are 4 cross represent a fused R matrix, and there is a fused R matrix, and this is another one, and this is a unfused R matrix here, and this this diagram is because of the project operator, these two can be cancelled by the definition, and this diagram becomes this one. And then, using the Yang-Box relation, we can find that there is a triangular here, and we can move this line to the right-hand side of the cross. And then we can find that there is also a triangular here, and we can move it to the right-hand side too. And then we add the project operator again in this way, and from subplot A to E, we can find that the fused transfer matrix indeed satisfies the Yang-Box relation. Sorry, pardon? Oh, one stands for the auxiliary space. The stand. The right. What? Sorry.
The right-hand side of the equation.
Right-hand side of the equation.
1/2.
1/2.
What is 1?
Oh, one is this one. This one. One. Yeah. This one spin. Oh, not the spin, but the no, yes, space, not the spin, space. Okay. We can find from this diagram, you can directly find the fusion is nothing but the entangle of two space. Okay. At the point of u equals to inhomogeneities, and the relation can be simplified as the homogeneous one. It's like this equation, and we have shown that Tu and the transfer matrix and the fused transfer matrix is commutative with each other. So we can write down the eigenvalue equation for the above relations. It's like this one, and is the so-called TW relation. Okay, and the lambda is a function of u, is a polynomial of degree n, and the same with wu. And it satisfies the asymptotic behaviors. Okay. Next, we have parameterized these two functions with its zeros, like this way. Now using substituting these two equations into the previous TW relation, you can directly obtain the constraints of the zero rules for lambda and for W. It's resulting in these two equations. Compared with the transitional beta-ansatz equation, these equations become two-sided. But we should come here, we should come here for the for the U symmetry broken case. The beta-ansatz equation is almost the same. Okay, then you can write the energy with its zeros. And to do the thermodynamic limit, we have to analyze the distribution form for the beta rules, for the zero rules. Now you can find that the R matrix satisfies the hermitation relation. It's like this way. And using this relation, you can get the hermitation relation of the transfer matrix. the same thing for the W operator, the W function. Right. Okay. By considering the hermitian relation of these two functions, and you can directly obtain the if Zj is zeros of the transform matrix, then is conjugation is also being zero rules, and the same with the Wj. Here is a numerical calculation of this of the zero rules for lambda and W, and we can find for the zeros, it form two line located at the imaginary part equals to 1 and minus 1. And for 1.5 is the W rules. So, oh, okay, sorry. This is for the ground state, right? Then you can substitute in the distribution form of the zero rules into the parametrization, like this way. Then you can do some calculations. Such you can define the lambda with the expansion of n. N is the system size, like this. And using when n tends to infinity, you can directly obtain this equation. This the rho j beta is the density of zero rules, and the rho w beta is the density for the W rules. And we have here we have used the previously the lambda theta times lambda theta minus eta equals to a known function, and we have take the difference of this function at two nearest inhomogeneous points, and obtain a constraint equation. It's this one, and by taking the constraint equations, substituting these two equations into this one, these two equations into this one, you can write down the constraint equations like this, like this, and you can directly solve it by Fourier transformation and obtain the densities of the zeros for different orders within. And you can by obtaining this, you can substituting this into the expression of the energy, and you can get the ground state energy, which is exactly the same with obtained by the algebraic beta ansatz. And substituting the density of the zero rules into the expression of the lambda function, and you can obtain the explicit expression eigenvalue of the transform matrix as the ground state. It is like it resulted here. After calculating the eigenvalue of the lambda function, we're here to calculate the W function. We have just obtained two sets of Bethe-Ansatz equations for the zero rules. Here we use this one, and we take the complex conjugation of this Bethe-Ansatz equation and times these two equations together and obtain a new one. And for this Bethe-Ansatz equation, you can take the derivative and logarithm of this equation and obtain the density of the W rules. It's the result is here, and similarly you can use this density and calculate the explicit expression for the W function. The result is here, and by substituting the lambda and Wj into the TW relation, you can obtain the relation like this. And we can, when u tends to infinity, we can find that there are two integral constants and can be fixed as 2 and 3. And by taking another limit when n tends to infinity, and you can find in this this term will turn to 0. So this term for the ground state can be cancelled, which is exactly the inversion relation. Okay, let's come to the thermodynamic parts. The method, the first thermodynamic property was achieved by Yang Zhenning and Yang Zhenping for the quantum burst gas, and then this method was generalized to the quantum swing chain models, and this method now known as the thermodynamic Bethe-Ansatz. And the free energy was finally encoded by a set of infinite number of nonlinear integral equations. And we should note that in an alternative approach, it's called the quantum transfer matrix method. Here we use this one. And for the quantum transfer matrix method, it comprises of two main components. The first one is this mapping, that Trotter-Suzuki mapping. You can use this map to map a 1D quantum system at a finite temperature, mapping to a classical system on a 2D inhomogeneous let's see. And you can find the free energy was expressed by the largest eigenvalue of the quantum transfer matrix. The second part of the QTM is you should express the largest eigenvalue of the QTM by the counter integral and nonlinear integral equations. Okay, we should notice that for QTM, only a finite number of NLIEs are needed. And besides this, you can use a transfer matrix renormalization group method. This is a very powerful numerical method to study the thermodynamics of the quantum swing chain systems. Okay.
this is just so I can understand the next bit. So the TW relation. So you're solving. So W is just the spin 1 auxiliary space transfer matrix.
Yes.
Is that?
It's auxiliary space is spin 1. Yes.
Okay. So far it's just an alternative version of beta ansatz for the T1 operator, but this is going to play a key part in your later approach to open systems. Is that?
Pardon, please. What is the key part?
Okay, maybe I should postpone the question, but it's the spin 1 auxiliary space transfer matrix, W, yeah?
Yes,
Okay,
yes,
good.
yes. That
Okay,
is
thank you.
exactly. Okay. Next, we will construct the TW relation of the quantum transfer matrix, and new NLIEs are obtained by the TW relation. Here is the model, and we have added an magnetic field here. And the Hamiltonian is constructed as this way. And for a small u, you can expand the transfer matrix like this way, which means the partition function is written as the trace of the exponential of the Hamiltonian. If we divide an n here, and when n tends to infinity or n very large, you can expand the exponential here like this way, and here the Hamiltonian can be obtained by the transfer matrix. In the right rectangular here is the transfer matrix, and it times n over 2 times, but here is n because you need to cancel the T0 here is also an operator, so there is n. And this is exactly the partition function. And by doing the partial transpose, you can reverse the direction of these arrows. And using the crossing relation of the R matrix, you can obtain this one. In the vertical direction is exactly the quantum transfer matrix is this. Okay, now we express the partition function as the quantum transfer matrix, and the quantum transfer matrix, when n tends to infinity, the largest eigenvalue is gapped from the others. So when n is also very large, you can just study the largest eigenvalue in here. Okay, here is the quantum transfer matrix we have obtained, and the free energy is expressed by the largest eigenvalue. Here is the TQ solution of the QTM. Here is the traditional TQ relation. Two has a homogeneous one, and here is functions related, and this is the beta ansatz equation. The difference is we add an factor here. Represent this is because when we add an magnetic field, which in QTM is just a twist in here. Okay. Next, we want to do these things in the frame of TW scheme. So you can write down the corresponding TW relation like this way, and also parameterize it with these zeros, Cj and Wj, and the associated beta and Sass equation. You can write down like this, like this. And then we introduce a normalized factor in here to keep when u tends to infinity, and this term is finite, but this function is finite. And by adding this eta, eta is I, imaginary I. You want to move the singularities or the zeros, which we will show later. Okay, and this is the normalized TQ and the associated beta and Sass. Here is the numerical results for the beta rules and the zero rules. The black one is beta rules, and the red one is zero rules. The blue one is the W rules. We can find they both satisfy a very good distribution form. The advantage for zero rules is when U symmetry is broken, this good structures also hold. Okay. After knowing the distribution form for the largest eigenvalue state of these rules, you can parameterize the lambda function as this way, and together with the W function. And then you can substitute in this parameterization into the TW equation and obtain the this relation. And the QU is a known function, is this, and the W is an unknown function. So all we need to do is to fix the epsilon bar here. And the epsilon bar u is analytic except some singularities on these two lines. And when u tends to infinity, and this is 0. That is why we choose the normalization factor to maintain these singularities on this x. Okay. By using the decomposition of the lambda function, you can directly obtain an integral representation for the log lambda u. And substituting this integral representation into the TW relation, you can obtain this nonlinear integral equations. And by solving these integral equations, you can directly obtain the lambda bar of V and obtain everything. And the free energy of this model also can be expressed by the epsilon bar. And here is the result, numerical results we have obtained. And we can find that these results are match with each other, and is very good. And for the SU3 case, the main idea is almost the same. For the SU3 case, the Hamiltonian is like this way, and the corresponding R matrix is the 9 times 9, and the corresponding quantum transfer matrix is this one. And because the limit of time, I will show it quickly. And the and here is the corresponding TW relations, because the because project operator is not one-dimensional, so you will obtain another auxiliary operator T2 here, and you got two sides of this TW relation. And these operators are commutative with each other, so we can write the relation with its eigenvalue functions. So the Fourier relation become these two relation. Again, we can parameterize these functions with its zeros like this way, and obtain the constraint equations for the zeros. And then by doing the normalized and analyze the distribution form for the zero rules, we can find it also possesses a very good distribution form for the largest eigenvalue state. By substituting this distribution form into the expressions, we got the expression for the for this specific state. You can parameterize it as this way. There are two lambdas and two w's. Okay. Again, we substituting the parameterization into the two TW relation, and you obtain these two relations. And we have to point out there are four unknown functions are introduced here. And for these unknown functions, their analytic is all analytic except some singularities on some specific x. And for the SUN case, in order to determine the eigenvalue of lambda u, you need to further introduce 2n-3 auxiliary functions. If you use the beta rules, the traditional beta rules, there is 2 power of n and minus 2 auxiliary functions. So it's a simplification. Okay. Now you can by using the decomposition of this lambda, and you can write down an integral representation for this two functions like this, and substituting this into the TW relation, and got a nonlinear integral equations. By solving these two nonlinear integral equations, you obtain the these four unknown functions, and obtained the free energy expressed by these two functions. Okay, let's back to the zero temperature case. Here we consider the open boundary condition with these two reflection matrix, and this matrix has a non-diagonal term, is a Xi term, which will break the UE symmetry. And these two K matrix satisfy the reflection equation and the dual reflection equation. And you can construct the double row transform matrix like this, and it also satisfies the RE relation. You can construct the transform matrix by using the double row transform matrix. And the Hamiltonian is obtained by similarly by the logarithm and takes a derivative of it. And we can find that there are additional term here, and is sigma x breaks the UE symmetry of the whole system. Similarly, we
Sorry, you have 2 minutes.
2 minutes. Okay. Okay. The method is almost the same. What I need to point out is the distribution form of the distribution form of the zero roots for for the system. We can find that even we break the UE symmetry of the system, the zero roots also satisfy a rather good distribution form. In the middle, this line is the boundary string, and this is the bug terms. Also, also possess very good distribution form. Okay, you can do the same thing just as the periodical case, just like it, and you can obtain the final result is this equation. And again, you can find when n tends to infinity, and these terms maybe can be cancelled, and it will regain the so-called inversion relation. A brief summary is we can obtain the exact solution of the model with periodical or generic open boundary conditions, and we can obtain the analytic expression for transform matrix and the W operator. And it can serve as a compelling proof of the validity of the emission relation. And the last, it is an efficient and easily extendable procedure to get the thermodynamics. Okay, that's all. Thank you.
Thank you for your talk. Do you have any questions?
So is there any simple explanation to explain why TW relation has a better distribution of the beta roots?
Actually, for the inhomogeneous TP relation, you may have many different forms. You can parameter one eigenvalue of transfer matrix into different forms by adjusting the inhomogeneous term. But however, if you parameterize an eigenvalue of transform matrix with its zeros, it's only one pattern. You just you use these zeros. It's no 任意性，it's no it's just fixed.
Actually, what I'm doing is, so you want to take some dynamic limit.
Yes.
So you need the beta roots to be good enough to have a continuous limit, right?
Yes.
So is that W the TW relation provides better this kind of roots or?
Yes, because the distribution form of inhomogeneous beta roots is always is not is generally complex. It's not on some straight lines. It may some there some curves, you know. So using the zeros is often a simple one.
Okay, thanks.
Maybe I want to ask you a question. So the advantage of the TW relation is that, for example, for the beta equation, right? If the system has U1 symmetry, you have this homogeneous beta ansatz equations, and you can do the thermodynamic TBA, right?
Yes.
But if there's no U1 symmetry, sometimes there will be a trouble, right?
Yes.
But if you do the TW relation, so how to say, so the zeros of the lambda of the function W is fixed, and it's a smooth function of the system parameters. So if
Yes.
so how to say, if at some point you have symmetry, but you add some, for example, in open chain you add some non-parallel boundary fields case, you still have a nice distribution for the zeros. I mean, so that is why if you want to do some calculations in the thermodynamic limits, so I think the zeros of the transfer matrix maybe is better than the base rules, especially in the case if you do not have a homogeneous decay relation.
Yes.
Maybe.
Okay.
Hello. Have you heard the words TT relations, heritable linear dynamics? Did somebody tell you that it's the same thing?
Sorry, I just heard the last word. So someone talks the same thing. Sorry. Can I beg a...
Okay. The words TT relations, heritable bilinear dynamics. Do you know these words?
TT relation.
TT.
TT.
Or T
The
system.
Furin relation, I think, is almost all the same thing, right?
So why do you use new letters?
So why? What? Why?
Why do you use new letters?
Oh, I see. Maybe just a name. you can call it a Furin relation or TT relation. I think it's just the same thing.
Okay. Have you other questions, but not about notation? Okay. Thank you for your talk, and bon appetit for everyone.